Okay, Bismillahirrahmanirrahim. So for today, we are going to discuss two topics of Sarifan that are the cantilever wall and the design of rectangular tanks, water tanks. So in Sarifan's topics, only these two, in Sarifan's syllabus, only these two topics we have to do. And for steel, first of all, let me write. For DOS, we have concrete portion as well as steel portion. So for concrete, we have only retaining wall and tank design. There are only these two topics. For steel, we have base plate, bracing design, and connection design. So these three topics are for the rushes portion, and for membranes portion, we have stringer design, we have floor beam design, and we have deck slab design. So for membrane, just try to follow examples 9.1, 9. In some books it is 9.3, and some it is 9.2 and 9.3. These three examples, they covered all these three topics in steel book, uh, steel structures book. For Sir Rash's part, these are comparatively simpler. The base plate and bracing, only the connection is a little bit difficult. So if you get any problem in this, just message me. We can do some meeting for this. But the retaining wall and tank, these are two major topics, and 20 marks, a paper of 20 marks would come from these. So we're going to discuss these topics. So first we have retaining wall. So what is retaining wall? Retaining wall is any structure, a wall, which is used to retain some material. For example, if there is a sand here, backfill of sand here, so we are trying to construct a road here. So we have to create this wall here, this wall. Otherwise, this sand would fall on the road. It has no support. So this we create this retaining wall to retain this sand, to stabilize this sand backfill. So retaining wall is a concrete structure, as well as we can also make retaining wall from stones as well. So what we are going to discuss, we are going to discuss cantilever retaining wall. So cantilever retaining wall is a concrete structure. This one like this. There are also gravity retaining wall that is only made of stones, etc. Like you would have seen in northern areas. So, but the major portion is cantilever retaining wall. The gravity retaining wall is very much simpler because we do not need to design anything. We are only going to apply some stability checks on this. In cantilever wall, we have to apply the stability checks as well as design the components. So cantilever wall is more difficult for this. So what is our given data? So for this cantilever wall or any retaining wall, only the sand, the soil profiles, etc. would be given. For example, we are given the height of backfill. For example, backfill we are given in this question, it is given 5.5 meters. So only we are giving this backfill height. For example, if this is our retaining wall, the only thing that we are given is this backfill height. This soil height is given 5.5 meters. The other thing, soil properties are given like phi, angle of internal friction 32 degrees, and allowable bearing capacity of soil, that is 180 kilopascals. And what is given? Yes, unit weight of soil, mass is 17.6 kilonewton per meter cube, and surcharge, the load applied on the soil, that is 3 kilonewton per meter square. This some load is also applied on soil. This we call as surcharge, that is 3 kilonewton per meter square. Rest of it we have to know ourselves. For example, if we are designing the concrete portion, we have to know its FC dash. Refresh we usually take as 20 megapascal, or it would be given Fy of steel for reinforcement is 420 megapascals, and the gamma of concrete, the unit weight of concrete is 24 to 25 kilonewton per meter cube. It depends, but on us, we can take any value between 24 and 25. And the last thing is alpha. Alpha is a coefficient of friction between concrete and soil. So this retaining wall is resting on soil, and it is made of concrete. So the friction between the concrete and soil, that is represented by alpha. So it is 0.45. We have to memorize this value. Either it would be given or we have to memorize this value. The coefficient of friction between concrete and soil. So this data is given. First of all, what we have to do, we have to determine the dimensions of this retaining wall. The dimensions. For example, what would be its height? This portion is known as stem. This middle wall portion is known as stem. This front portion away from backfill, this is known as toe, and the portion on which the backfill is resting, this is known as heel. So these are three main portions of retaining wall: toe, stem, and heel. And this whole base, which includes heel and toe, this we can simply call as base or base slab. This is slab, so base slab. So these are three portions: stem, heel, and toe, and we can call toe and heel collectively as base slab. So first of all, we have to determine the height of stem. The height of stem we have to determine. So we are given this backfill as 5.5 meters. We have to assume some value of this freeboard. So for example, if this is 5.5, we can assume this has 0.5 meter. So we can call the height of stem as 6 meters. So it depends on us. We can assume any value of this freeboard, and we can determine the height of stem as 6 meter. 5.5 was given value of backfill, and the 5 meter 0.5 meter we have taken assumed ourselves. So this is how we can determine the height of stem. The second thing is the thickness of stem at the top. So this is T stem at top. So for top, we know that there is zero bending moment and shear force at the top. So for this zero bending moment, ACI has recommended that 0.2 meter of minimum thickness we use. The stem at top should be of minimum 200 millimeter. Actually, we can reduce this to zero because we know that there is no bending moment or shear force at the top. But due to some factor of safety, we have to at least provide 200 millimeters or zero point 0.2 meters of thickness at the top. So this is our guideline. And the thickness of stem at the bottom. So we have thickness stem at the top as 0.2, TS at bottom, thickness stem at bottom. So for this, we are given this guideline that T stem at bottom is between H by 10 to H by 14. So T stem at bottom is H by 10 to H by 14. H by 10 is approximately 0.6 meters. H by 14 is approximately 0.4 something meters. So we can take thickness of stem at bottom as 0.4 meters. This is 0.43, I think, but we can assume this as 0.4 meters. These are only guidelines, not hard and fast rule. So 0.4 meters. So this is how we can determine the dimensions of stem. These are some guidelines. Height we have to determine from backfill. Top we are given as 0.2. Bottom we can determine from H by 10 to H by 16. Okay. So afterwards, what we have to determine? We have to determine this length of heel and this length of toe. That we have to determine. That what is the length of heel and what is the length of toe. For this, we have to determine this whole base width. This whole base width. If we have an idea of this whole base width, we can divide the total base width into heel and toe. So for this base width, we are also given this guideline that it should be between 1 by 2 to 2/3 of height. The space should be between 1 by 2 of height, that is 6, to 2 by 3 of height, that is so one half of height, that is 3 meters, and 2/3 is 4 meters. So our base should be lying between 3 to 4 meters. It should lie between 3 to 4 meters. So if we assume this length of heel as 2 meters, that we are assuming ourselves, and toe as 1 meter, so that will be 3 meters, and the middle portion is 0.4 meters. So our length of base width would be 3.4 meters. B is equal to. We are assuming ourselves. So 3.4 meter is lying between 3 and 4. So that is fine. We can take this as. So from this base width, we have also determined the length of heel, that is 2 meter, length of toe, that is 1 meter. That we are assuming on the base of this base width. Just one thing we have to take in mind, that length of heel should be greater than length of toe. That length of heel should be greater than length of toe. The toe should not be greater. So that we have all determined. And the last thing, we have to determine this base thickness. This thickness of base slab, this base slab thickness. So again, we are given this guideline that it should be between h by 10 to h by 12. So TB, thickness of base, should be between h by 10 to h by 12. So h by 10 is again 0.6 meter, h by 12 is again something like 0.5 meters. So we are assuming thickness of base as 0.45 meters. That is multiple of 75 millimeter. So we are assuming this thickness of base as 0.45 meters. And this is not very critical. In later on, we are again going to devise this thickness, base slab thickness. So now we can simply take the minimum value 0.5 meters, and later on we can revise this. So this is how we have to determine the whole dimension of the retaining wall. Any issue in this part? First, we have to determine the stem height, then stem top and stem bottom. Then we have to determine the total base. From this base, we are going to assume some heel and toe values, and check whether these add them and check whether the sum lies between the given recommended values. And finally, we are going to determine the base slab thickness. Any issue?
No, brother.
All right.
No.
So one thing I forgot, that this is backfill at the backside, and we are also given some front fill here. So the front fill height is 1.3 meters. Some sand is lying also on the front side of the retaining wall, and its height is 1.3 meters. On the back side, its height is 5.5 meters. So this is all. We are going to use this front fill in the later steps. So after determining the dimensions, we have to determine the vertical forces in this retaining wall vertical forces. So if I draw this again, we have this backfill on the back side, we have this front fill on the front side. The backfill height is 5.5 meters, the front fill height is 1.3 meters, and the length of heel is 2 meters, that we have determined. Length of toe is 1 meter, and the height of this whole retaining wall, the stem of the wall, is 6 meters. This is 6 meters, and 0.2 on the top and 0.4 at the bottom, and total is 3.4 meters total base slab. So these are dimension of base slab, retaining wall, sorry. Now we have to divide this retaining wall into different parts, and we have to divide this into simple geometrical figures like rectangles and triangles. So for this, we have this trapezoidal section. We are simply going to divide this into two parts. One is rectangle and one is simple triangle. So in the rectangle part, the top width is 0.2. The obviously the bottom would be again 0.2. This is a rectangle. So this if this hole was 0.4, so zero point 0.2 is left here. So here would be left again 0.2. So triangle base would be also 0.2. So now we are going to number these segments. So for example, this one we can name as 1, this main stem. This triangle we can name as 2, and this base slab we can name as 3. We can divide this surcharge into also two parts, a rectangle and a sorry. We can divide this backfill into two parts, a rectangle and a triangle. So the rectangle portion we can call as 4. The triangle portion we can call as 5, and the front fill we can call as 6. And the last vertical force would be from surcharge. This on top of this S is equal to 3 kilonewton per meter square. So this would create a force. We can call this force as 7. So these 7 vertical forces are present in this retaining wall. First is, so if I write this, the first one is main stem. This main stem or rectangular stem portion, this main stem. The second one is this triangular stem. We can call is taper stem. The tapered portion of the stem, tapered portion. The third portion is the base slab. So third portion is base slab. The fourth portion is this backfill, rectangular backfill. The fourth portion is rectangular backfill. The fifth portion is this triangular or tapered backfill. We can call it as tapered backfill. The sixth portion is, you can say this is the rectangular front fill on the front side. So rectangular front fill. And the last portion we have is surcharge. The load acting on top, this surcharge 3 kilometer per meter square. So these all forces are present. So if we have to determine these values, simply we have to multiply the gamma of the whatever the material is multiplied with the area, because we are going to determine the weight like this. So for example, this main stem portion, it is a rectangle, zero point 0.2 meter is its width and 6 meter is its height. So simple, it is also made of concrete. So simple for its weight, we can simply multiply gamma of concrete multiply by 0.2, it is its base, and 6 meter is its height. Simple multiplication, gamma of concrete we have taken as 24 times 2 times 6. So this way we can calculate the weight of this concrete main portion. Similarly, for this triangular portion, that would be gamma of concrete multiplied by area. So area of triangle is 1 by 2 base into height. The base is 0.2, height is again 6. 1 by 2 into 0.2 into 0.6. So this way we can get the taper stem weight. For base slab, it's again rectangular portion. The thickness is 0.45 meters. So gamma of concrete, again it is made of concrete times 3.4 times 0.45. The fourth portion is we have of sand, this backfill, rectangular backfill. So 2 meter is its width, 5.5 is its height, and gamma we have going to use gamma of sand here because it is made of sand. So 2 meter times 5.5 its height. The tapered backfill, the triangular one, so gamma of sand times half into base. Base is again 0.2, height is 6. So actually this height is, sorry, the actually, oops, its height is 5.5 meters, not 6. This we are taking this backfill. So actually this portion is not equal to zero point 0.2. This is a little bit less than 0.2. But we are assuming that we can simply take this as 0.2. If we have to be more accurate, we can make this triangle and compare these two similar triangles. but simply we can take this as 0.2. There's not much difference. Very small value. This is very small value. So for rectangular front fill, we have height as gamma of sand times we have height as 1.3 and width as 1, the length of 2. And finally, the surcharge. The surcharge is simply S times the length on which it is acting. So it is acting on 2 meters, so S times 2. We have S as 3 meter into 2, so it is 6 meter, 6 kilonewtons. All right, this way we can calculate all the forces of all the rectangular forces. So after calculating these rectangular forces, we can simply sum these rectangular forces this way. We have calculated all the rectangular forces like this. So after calculating these rectangular forces, we have to sum these rectangular forces. So first we have to sum without surcharge. That first of all we have to we have to take all these values and calculate its sum without surcharge. So first would be our without surcharge total vertical force. Then we can add with surcharge. So that would be without surcharge WS without surcharge plus 6 surcharge force. Surcharge force is 6 kilonewton. So this way we can calculate without surcharge the sum of all the forces except surcharge and add surcharge in that sum will get with surcharge. Any issue in this vertical forces? Okay. So after calculating the vertical forces, we have to determine the lateral forces or horizontal forces. So again, if I draw this retaining wall, so this is our backfill and this is our front fill. So this surcharge is acting on this, that is S. So what would be the lateral force of the sand? The lateral force of the sand is determined by its active or passive earth coefficients. For example, this is our backfill. This green portion is our backfill. For example, if a retaining wall was moving towards backfill, a retaining wall was moving towards backfill, then we are going to say that the soil is under passive earth pressure. We are going to use CP coefficient for that portion. But
Repeat,
in
bro.
this case,
I don't understand.
sorry,
Repeat it, bro. I didn't understand. Bro.
I cannot understand.
Bro, about the retaining wall, what you're explaining now, could you repeat it here? And the lateral forces, I'm talking about the lateral forces in the CP, the one you're saying now, how it's acting.
How it's acting? I didn't get your question. What are you saying? One moment. Yes.
Bro,
Hamza that
the horizontal forces, just
Hamza
from the
that
horizontal
uh,
forces.
yeah, Hamza that he's asking about that CP. Why you taken CP? Just explain it again.
Okay. So actually, so for example, this is our retaining wall. If there is this backfill, if this portion, the retaining wall, is moving away from this backfill, what would happen? That this sand would exert this pressure like this. Isn't like this? If the sand is exerting this pressure on this retaining wall, the retaining wall would move towards the left side. In this case, the sand is actively applying pressure on the retaining wall. Does this make sense? That this sand is applying this pressure on this retaining wall, and due to this retaining wall is moving away from this sand. So in this case, we are going to say that the sand is applying active earth pressure. Active earth pressure, and we are going to use coefficient as Ca. The opposite case is that the sand is lying like this and the retaining wall is moving towards this sand. What I was saying before. The retaining wall, due to some load, for example, this load is created like this, due to any kind of load. For example, this retaining wall is moving towards this sand. So now in this case, the sand is simply lying here. It is not moving. It is not applying any force on this retaining wall. But the retaining wall is lying on applying this force on the sand. So in this case, we are going to say the sand is acting passively. So we are going to use passive earth coefficient for CP. Okay, simply if the retaining wall is moving towards the backfill, we are going to use CP like this. If the retaining wall is moving away from backfill, we are going to use the coefficient CA. Is this fine?
Yes, it's fine, bro.
Okay. So the formula is simple that the CA formula is 1 minus sine phi. The phi is angle of internal friction and the divide by 1 plus sine phi. So this is the formula of CA. The CP formula is its inverse, that 1 over CA and 1 plus sine phi over 1 minus sine phi. And just remember that it is always greater than 1. CP is always greater than 1, while CA is always less than 1. If you somehow uh, forgot these signs, that should minus be on top or should plus be on top. So simple calculate this formula, calculate using this expression. So if this is less than 1, so automatically assume that is CA. If it is greater than 1, then that is CP. So this way I have remembered that you can remember the formulas. So after this, now in this case, we have this huge amount of backfill on the backside. This is 5.5 meters and only some small amount of backfill on the front side, that is 1.3 meters. So what the backfill would cause, it would cause the retaining wall to move away like this. So in this case, what is happening in this backfill portion, that it is applying active earth pressure on the retaining wall. It is actively moving the retaining wall away from it. Okay, and what is happening on this front fill, that this retaining wall is falling on top of this front fill. So we're going to use CP coefficient for this front fill. Due to this movement of retaining wall, we have determined where we have to use CA and where we have to use CP. Is this fine?
Yes, brother.
Okay. So afterwards, what we have to do is we have to calculate this lateral force of this soil. So the lateral force of the soil, for example, if this was some liquid, this is a tank, water tank, and it is filled with this liquid. So what would be its lateral force? That is simple. Pressure force is simple like this, and it would be gamma times h. For example, this is the height of liquid, and gamma is the unit weight of the substance. So the force exerted by this would be simple gamma h. Now in this case, we are going to use the force exerted as gamma of sand times this h. Now remember, this h is not 5.5. This is h is 5.5 plus 4.5. We are going to take this h till the from the top of the backfill till the bottom of the retaining wall. So if I write here as h is 5.5 plus 0.45, that is 5.95. So gamma of sand time h, this is the pressure at the bottom, and we are going to multiply it with the coefficient, that is Ca. So the pressure at base would be Ca times gamma h. This would be soil pressure, and what would be the surcharge pressure? That would be simple rectangular, and it would be simple Ca times S. The simply Ca times SH, that would be the this surcharge pressure. Okay, so in the same way for the front fill, we have this passive earth pressure. So the passive earth pressure would be again the same, gamma s into h. Now here the h is, we can call this as h1. The h1 is, we have 1.3 plus 4, 1.3 plus 0.45, 0.45. That is this thickness of base, 0.45. So that is 1.75. So gamma s times h1 multiplied by cp. So this would be the pressure at the base of this uh, front wheel. So after calculating this pressure, how we are going to determine the forces, because we need the forces. The forces are simple, the area of this pressure diagram. For example, if we call this as H1, the force is generated by soil, active force, this force as H2, and this passive force as H3. So H1, H2, H3 are simple areas of these. So H1, H1 triangular area is half into base into height. Half into base we have Ca gamma s h. This is our total base. Into height we have as again h. So simple, we have to multiply this. We'll get this active earth force. For same in the same way, now we have this rectangular portion. So simple, the area of rectangle, base into height. So Ca times s is base. We height as we have h. So this way we can get the h2 value. And for h3 value again we have triangle. So half times base we have Cp gamma s h1, Cp gamma s h1 into height we have as h1. So this way we can get the all the lateral forces of the backfill and surcharge. Okay, any issue in this? This way we can get Ca and Cp we can calculate first. Simple, using 1 minus sin phi or 1 plus sin phi, and we can calculate h1, h2, and h3. H1 is 5.95, h2 is, this is 1, h is 1.95, 1.5. Issue in these little forces. Okay, afterwards, after evaluating these forces, we have to apply some checks. First, we have to apply overturning check. Second, we have to apply sliding check. And the third, we have to apply bearing check. So we are going to apply all these three checks. And for overturning, our factor of safety is 2. For sliding, our factor of safety is 1.5. And for bearing, our factor of safety is 1. So this way we have to apply these three checks. First of all, three checks should pass. First of all, we have overturning. The overturning, we have to calculate the overturning factor of safety is, that is resisting moment, that MR is resisting moment over MO or MD disturbing moments or overturning moments. So this, we have to calculate the resisting moments and we have to calculate this overturning moments, and if this take the ratio, and if this ratio is greater than 2, our check is satisfied. Otherwise we have to change the dimensions of the retaining wall. So first of all we have this uh, restoring moment. So for restoring forces, all the forces we calculated before, all the vertical forces we calculated before, we are going to use all these. So for example, we calculated the vertical forces, all these forces we calculated before. Now for the retaining, for the restoring moments, just we have to do is multiply this value of force with its moment arm. So moment arm we can calculate from this figure. For example, if we look at this figure, or if I draw this again, So this is our backfill, and this is our front fill. This is our 1 meter. This is our, if I divide this into two portions, 0.2 meters, 0.2 meters, and this is our 2 meters. So these are simple values of the stem and heel and toe. Now we have to calculate the moment arms. So what where we have to take the moment arm? We have to take the moment at the toe value. That at the bottom of the toe, we have to take the moment arm. So for example, for our first force, we can call this as first force. This main stem force. This one main stem. The first force. What would be our moment arm? Moment arm would be our. It would be simple like this. That 1 plus 0.2 over 2. This half length of this portion, 0.2 over 2 plus 1, the toe length. So that would be like 1.1 meters. So its moment arm would be 1.1 meters. This is our moment arm. The second portion is this triangular portion, this portion. So what would be its moment arm? Its moment arm would be like this. So it would be like 1 meters plus 0.2 meters of main stem plus one third of this portion, one third of this green portion, because it's a triangle, so its centroid will be lying at one third. So that would be like 0.2 over 3. So this way we can calculate the moment arm of this second uh, stem portion. The third portion is we have this of base slab. For example, this we have of base slab. So simple, we know the base slab is of 3.4 meters, but to its moment arm, that would be simple 3.4 over 2, because it's a rectangular portion. So that would be a 1.7, and this would be like something 1.2 and something, approximately 1.23, something like this. So you can calculate this value. And the fourth one is we have of this uh, backfill of sand. The backfill of sand, the length would be like this. That would be like 1 meters plus 0.2 meters plus 0.2 meters. This is all the stem portion and the toe portion, and plus this 2 divided by 2, this 2 portion of this uh, backfill divided by 2. So it will be like 1.4 and plus 1, 2.4 meters. Fifth portion we have of this tapered backfill, again its length, that would be like 1 plus 0.2 first stem portion and 2/3 of the second stem portion by 3 of 0.2. Why we are taking this to by 3? Because remember this centroid of triangle is always lying where its mass is most. So if we take this triangle, so obviously its mass, its centroid should be lie between this portion. So this would be its moment arm. Fifth portion, the sixth portion would be this, and its moment arm would be simple. 1/2. The one portion, 1 meter on 1 meter portion it's acting, so its moment arm would be zero point 0.5. So this one would be 0.5. And the last, for this surcharge, we do not need to calculate moment arm now. We can calculate moment arm later on. We are not going to use surcharge in this restoring moments. So our restoring moment would be MR would be, that would be V1 times its length. So that is we can call as X1 plus V2 the taper stem portion times X2 plus V3 is our backfill base slab portion times X3 plus V4 is our backfill portion rectangular times X4 plus V5 is our tapered backfill times X5 plus V6 are front fill times X6. Simple, multiply the weight of the forces with the moment arm, we'll get this restoring moment. So after this restoring moment, we have to calculate overturning moment. The overturning moment is, again, we are going to use the same thing. Just now we are going to use the lateral forces. For example, these are lateral forces H1, H2, and H3. We are now only going to use H1 and H2 because H3 is also a restoring force. It is acting against H1 and H2 in opposite direction. But we are going to neglect this value for conservative design. So our H1 value would be from the bottom of the toe, its moment arm would be simply this H by 3. This is H over 3 because it's a triangular, so its moment arm would be H by 3. And for this H2, its moment arm would be simple H over 2. Where H is, we have H as 5.95 meters. So for restoring moments, for this disturbing moments, overturning moments, we have H1 times Y1 plus H2 times Y2. Where Y1 we have as H by 3 and Y2 we have as H by 2. Just we have to get these values from the figure. H1 and H2 we have already calculated, and this way we can get resisting moments or restoring moments and overturning moments. So afterwards, what we are going to use, we are going to simply apply the formula, that is restoring or resisting moments over overturning moments. So its answer should be greater than 2. If it's greater than 2, then that's fine. So if we look at this, so these were two restoring moments, these were two overturning moments, and these are all the restoring moments without a surcharge. Remember, we are going to neglect the surcharge in restoring moments, and we are going to neglect the passive earth pressure in overturning moments. So after dividing them, we'll get the value as 2.92. 601 divided by 206, so almost 3 value we'll get. So our 2.92 is greater than 2, then that's fine. That this check is satisfied. Any issue in this?
No, brother.
Okay. So the second check we have to apply is sliding check. So again, this in the same way, we are going to calculate factor of safety. That would be uh, res- resisting or restoring forces. Now we are only going to use the forces, not moments, divided by the sliding forces. So it should be greater than 1.5. This factor of safety should be greater than 1.5. So first we have this restoring or resisting forces. So our resisting forces would be simply, if I write as Fr, so all the vertical forces what were acting, all these vertical forces without surcharge. Remember, we are going to neglect surcharge for both overturning and the sliding checks. We are going to neglect this surcharge. So all the forces, all the sum of forces, we are going to multiply this with the coefficient of friction alpha. So alpha times V without surcharge. Simply whatever the sum of the forces was without surcharge, multiplied with the alpha coefficient of friction between the soil and sand. So alpha is 0.45. We have to memorize this value, or maybe it would be given. And this way we can get the restoring forces due to weight, and the second restoring force is due to this H3. This H3 is moving against this is H1 and H2. It is opposite to this, so it would try to stop the sliding. So that is, so it would also fall in resisting forces. Simply alpha times Vs plus H3. If we add them, we'll get this resisting forces. The second is we have this sliding forces. So the sliding forces are simple Fs, that are H1 plus H2. Whatever the forces H1 and H2 we calculated before, simply add them. These two forces. No need of movement arms. simply add this H1 and H2. The addition of these forces would give us this sliding forces. Now our factor of safety is this FR resisting over FS sliding. So if we calculate these forces, our sliding force was 101, 95 was H1 and 5 was H2. And our restoring or resisting forces was 225. So almost 2.25, 2.23. So our factor of safety comes as 2.23. It is greater than 1.5. That is fine. Okay. So this is our second check, the sliding check. Any problem in this?
No problem, bro.
Okay. So our last check is the bearing check. We have to determine that whether the soil is strong enough to take the weight of turning wall and the backfill or not. So for this last step, we have to determine this bearing capacity. We have to determine this bearing pressure and compare it with the bearing capacity of the soil, allowable bearing capacity that was given in the question. So for bearing, now we are going to do this check two times. First, we have to do this for without surcharge, and second time we are going to use this with surcharge. So we calculated surcharge only for this check, that for only surcharge would be used in this bearing check, not in overturning and not in sliding. So for bearing check, we have determined the bearing pressure developed by this putting under we have determined the bearing pressure developed under this footing. So it would be like something like this trapezoidal, something like this trapezoidal. So we are going to name this coordinate as y1, this one as y2. So if you remember, we are going to use the same concept in the second case of base load also in the steel portion. So our y1 should be P over A, force over area plus My over I. Similarly, y2 would be P over A minus My over I. And we can also write this as P over A as P over A plus M over Z, where there's Z is equal to I over Y. Z is our section modulus. It is equal to moment of inertia divided by the distance from centroid to the outermost fiber. Y, sorry. So P over A plus M over Z, and similarly here we have P over A minus M over Z. Z is our section modulus, A is our area of footing, P is the total load acting on it, vertical force, and M is the moment generated. So now we have to know we have to determine where the resultant force is acting, where this P is acting. So for example, if we put this like this, that P is acting here. So now we have to determine its length from this outermost portion, from this base of toe, that would be our X, and its length from the center of base. The center of base, its length would be E. So the centricity of this load from the center of the base. This is B by 2, the center of the base. Half P here and B by 2 here, center of the base. So the centricity of the load from the center of the base, we'll call this as E. So our moment finally would be simple P into E. So P, if we multiply P into E, we'll get our resultant moment. Okay, so first we have to determine determine this A and Z value. So simple A would be simply B times 1, that we are assuming that the retaining wall is of unit width. So we have B of 3 meters, so our area would be 3.4 meters square. And Z value is simple B square over 6. We have to memorize this, B square over 6. So 3.4 square over 6, we can get some value of this section modulus. So we have to memorize these things. We have calculated this one. Now we have to calculate this X value. Using this x value, we can calculate this e value. Using this c value, we can calculate this m value. And if we have calculated this m value, we can simply plug in this value in this y1 and y2 formula and calculate the bearing pressures. So we have P or V, it is the same thing without surcharge. So without surcharge, our value was, this is without surcharge, the vertical force is 306 kilonewtons, 306 or whatever the value is. Now we determine this x. The x is resisting moments minus overturning moments divided by v, this v or this p. So the resisting moments we calculated before 600, I think. This one, resisting moments or restoring moments are 601 minus this overturning moments are 206 divided by 306, this v value. So this way we can calculate the x value. X value is, remember, from the toe, the bottom of the toe. So after calculating this x value, for e value, simple, the total length is b by 2. If we subtract this x value from b by 2, we'll get this e value. So x e value is b by 2 minus x. Simply by this way we can get the eccentricity, and finally the moment would be p times e or v times e, whatever this. So this way we can get these values, m and e. Finally our y1 would be, the bearing pressure would be p over a plus m over z. We know p, we know m, we know a, and we know z. And y2 would be p over a minus m over z. So if we check these values, our p over a plus m over z would come as 155 and other is 25. 155 kilopascals and this is 25 kilopascals. So our now factor of safety would be simply this allowable bearing capacity ABC divided by this larger ordinate. We have y1 155, y2 25. Simply we divide this by y1. So our allowable bearing capacity was 180 divided by 155. Its answer would come greater than 1, so that's okay. Our check is satisfied. So for bearing capacity only we need factor of safety 1, so it would come as 1.16. So that our check is satisfied. So after this, for with surcharge, the second portion is with surcharge. So we are going to use again the same things or same things. Just the force we are going to use as 312. The without force surcharge force and the sum of this surcharge force. So 306 plus 6, that is 312. So our force would be 312. The second step would be our x value. So x value would be restoring moments minus overturning over p or v. So now this, but just the single difference is this, that 601 was our restoring moment. In this moment we are going to add this moment of surcharge as well. This surcharge moment. We calculated this force before. We calculated this force as 6. So now we are going to add this moment as well in this. So 6 times this length. So this length is again the same. 1.4 is till this point, and the length of heel is 2 over 2 and divided by 2. So it is again in the middle of heel. So that would be 2.4. So 6 into 2.4. Simply we are
Bro, can you
just
repeat for the surcharge?
okay. So for example, this is our backfill. We are assuming surcharge is acting on top of the heel. This is surcharge is 3 kilonewton per meter square and is acting on top of the heel. So this is UDL. So if we calculate this equivalent force, what would be its equivalent force? That would simply this 3 multiplied by this distance. This is 2 meters. Like we calculated earlier, this weight. So 3 into 2, that would be 6. and its moment arm would be from this portion. So we know this is 1 meter, we know this is 0.4 meters, and this in the middle we know this as we'll take the half of this 2 meter. So 1.4 plus 2 over 2, and this way we can calculate the moment arm 2.4. Simply multiply the 6 with the 2.4, we'll get this historic moment. Okay, overturning moment would remain same, E would remain 312, and afterward E is simply B by 2 minus X, and M is simply P into E. So afterwards simply our Y1 is P over A plus M over Z. A and Z would remain same. Y2 would be P over A minus M over Z. So if we calculate this value, they would come almost exactly same. Just a little bit different would be there. So our this was 154.6 and 29. So 154.6 and 29. So almost same values. So if we calculate this factor of safety again, so allowable bearing capacity over this Y1 larger ordinate. So 180 over 154. So it is also greater than 1. That is fine. Our check is satisfied. So these are all three checks. Any issue in this?
No.
All right. So if the question of gravity wall is asked in the paper, I in the starting I said that there are two types of walls in the course. First is gravity wall, and the second is cantilever retaining wall. So for gravity wall, up till this portion, the question is finished. That for gravity wall, we are going to do up till this part only. Now that this next part we are only going to do in case of cantilever walls.
Bro,
Yes.
if he asks, there is two layers of soil, what the
Okay. Okay.
difference would be?
Only the difference would be the soil pressure. For example, this is our pose. This is our first layer of soil. This is our second layer of soil. Okay. So its phi value is pose 30. Its phi value is pose 40. So if the phi value is different, what would be different? Our CA value would be different. So our CA1, the CA for first layer would be 1 minus sine phi or 1 plus sine phi. Similarly, the CA of second layer would be 1 minus sine 40 or 1 plus sine 40. That's phi value of that layer. So this way our CA value would be different for both layers. After the CA values, now we determine this pressure forces. So for the first layer, the pressure force would remain same like this. The bottom coordinate would be CA1 times gamma S1 times H1. For example, this is H1, and the unit weight of this soil is gamma S1. Unit weight of this soil is gamma S2, and this is bottom till this bottom H2. Okay, this way, this we have already done in the previous portion like this. As we are going to use this CA1, gamma S1, and H1. Now the second portion is of this second soil. So its ordinate would be CA2 times gamma S2 times H2. We are going to use the ordinates of that layer for that portion. For example, this is our this portion. So the this ordinate would be CA2 times gamma S2 times H2. So this way we can get this value of this portion. Now for this portion, we are going to increase or decrease this value. We are not going to take this value as CA1 gamma S1 H1. We are going to take this value as CA2 gamma S1 H1. Simply we are going to change this coefficient of little coefficient into CA2. Okay. Okay. That on the top it was force 10 meters. Suppose this pressure is 10 kilopascal. On the bottom, suppose this gamma is, Ca1 was 10, or suppose this was 1, and this is 0.8. So if the pressure on top was 10, now the pressure at the bottom would be times zero point 0.8, so it would remain as it would decrease to 0.8. So this way we have to take this difference values. And this was for the soil. For the surcharge, this is similar procedure. For example, this is Ca1 times S. This is Ca1 times S, and for the bottom layer, it would be Ca2 times S. So for whichever layer we are calculating, use the Ca value for that layer only. Okay. So this way we
Okay,
can get this.
thank you.
Yes, after calculating this, we have to determine these forces. This would suppose we call this as H1. This we can call this as H2. This we can call it as H3. This as H4, and this rectangular portion as H5. So now in this case, our lateral forces would increase. And similarly, we have to calculate all this moment arm for this. So that would be a bit difficult question if 2 layers would come. So afterwards, after these all these three checks, we are going to design the portions. For these are for cantilever retaining walls only. So for designing, first we have to design the stem, the topmost portion. We have to determine the toe. We have to design the heel, and we have to design the base slab. So this four portion we have to design for this cantilever retaining walls. The first we have is stem. So for stem, if we look in this portion this way, so for stem, the critical moment section occurs at the face of the stem. This thing. So a critical moment would occur at the face of the stem. So whatever load we are going to take, we are going to take only up to the face of the stem. Previously, if you remember, we took the loads up till the bottom of the retaining wall. But now in this case, we are not going to take the boat till the bottom of the retaining wall. We are only going to take the load up till the top face of the stem. So for a moment, we are going to take the loads up till the top face of the stem. And this for the shear, we have to calculate this D value, the effective depth. So after calculating this effective depth, we are going to take the shear value, the critical shear value at the distance D from the top face of the stem. At the distance D from face of the stem, we are going to calculate the critical shear. So if I draw this again, so our forces are like this. Till the top of the stem, what would be our forces? That this would be like this. Now what we have as H, we have H as only this portion. So H should be our 5.5 meters. Remember, H is our 5.5 meters, the length of the height of the backfill. We are not going to take this 0.5 meters. We are going to ignore this portion. So our H value is 5.5 meters, the height of the backfill. Now this H1 force, what would be this H1 force? The H1 force would be half into base into height, half into base. The base is again the Ca into gamma S into H, where this H is 5.5 meters. Remember now H is 5.5 meters. So half into base into height, CAS into H, so sorry, CMA gamma S into H times H. So this way we can say, in the same way we can calculate H2. The H2 is our rectangular portion of the surcharge. So our H2 value is this Ca times S. So Ca times S times H based into height. So this way we can calculate this H1 and this H2. Okay, now we have to take these moments. We have to calculate these moments. So for this moments, simply determine the moments arm. So for this moment arm, as the critical moment is at the face of the stem. So we are going to take the moment arm from the face of the stem. So for H2, it would be H over 2, simply half of the H value. For H1 would be H over 3. So finally our MU value would be 1.8, 1.6. It is our factor of safety times H1 into H over 3, its moment arm, plus H2 into H over 2, its moment arm. Fine. This is how we have to calculate the this moment, applied moment on this stem. This way. So any issue with this? We have to calculate this way. We have to calculate the moment.
Brother, this factor always 1.6.
Yes, for moments it is one. For retaining wall it is 1.6.
Okay, brother.
For liquid water structures we are going to take it as 1.7. In water tank we are going to take it as 1.7. So this is our moments. For shear, again the factor of safety is 1.6. Now the formula is simply a bit different. Just simply memorize this formula. That is H1. This is our triangular force times H minus D over D whole square plus H2 times H over D minus D. In this portion, they have written H1 into this H1 and H2 values they have changed. They have taken H1 as rectangular and H2 as triangular. But if you use, we are all from the first step, we are taking this as H1 and H2. So take these and H1 H2. Just remember that for the triangular portion, we'll going to multiply it by square. For rectangular portion, we are going to simply multiply it by no square. So simply this way we can get the shear, applied shear. And this thing D, how we have to calculate this D value. For example, this is a retaining wall. At the top, we know this height as 0.2 meters. At the bottom, we know this height as 0.4 meter. So the D value at bottom, D value at bottom, D value at bottom would be 400 millimeters minus this clear cover. For clear cover, we are going to take 75 millimeters and minus half die of bar. For example, if we are taking 25 number bar, because reinforcement is quite much higher in this retaining wall, so we're going to take 25 bar and divide by half. So the D value would be simply 400 minus 75, that is 325 minus 12.5, that is 312.5. So this way we'll
Bro,
get
repeat it, please. Repeat it. How to calculate D?
D. So if you remember PRC1, for example, this is our concrete. So the D value is the effective depth of this steel layer. What is this D value? This is the effective depth. This is from the top. So we know this total height as 4 meters. At the bottom, what is this height of the concrete? This is 400 millimeters, 0.4 meter. This is 400 millimeter minus this clear cover of this parts. So for clear cover in retaining wall, we use 75 millimeter clear cover minus this half die of bar. D is still the half of the bar. So we are taking this 25 millimeter bar. So 25 over 2. That is 312.5 millimeters. Okay, this is the D value at the bottom of the retaining wall, bottom of the stem. So what we have to actually determine the d value, we have to determine the d value at the d depth, at the critical section. We have to determine the d value at the critical section. If the d value here was like this, I have shown this as green. This is the d value. This is 312 millimeters. So at this section, it would reduce somewhat. So we have to calculate the d value at the critical section. So for the d value at the critical section, we have to determine first of all what is the width of the critical section. This thing. So how we are going to determine this thing? Simply by similar triangles. If I join this, if I make this whole a single triangle, similar triangle, we know this length is 6 meters from this bottom to this, from this to this, we know this length is 6 meters. So if it is clearly visible, if the thickness of the stem is decreasing from point 2 point 4 to point 2, I mean that it is becoming half. It is becoming half in 6 meters. So what would be this length? In how much length it would go from point 2 to 0? Again, it would be 6 meters. Okay. You can also calculate this by similar triangle that assume this value as x and compare these two triangles and all this. But in this case, it is clearly visible that from it is the thickness is becoming zero point 0.4 to zero point 0.2. It is becoming half in some length. For example, it is becoming half in 10 meters. So from half to 0, again it would become in 10 meters. So that is simply obvious thing. So or you can also do this but similar triangle. For example, this x over 0 0.2 base over height is equal to this whole larger triangle. The larger triangle is bases we have as x plus 6 over 0.4. So if we evaluate this x value, it would again be 6. Okay, so afterwards, after we calculated this x value, now we have to determine this value. We can name this as y value. So again, this similar triangles we are going to use. For example, y over this black triangle. Okay, y over this black triangle. Black triangle is the width of black triangle is 6 plus this 12 minus total is 12 length minus d. So for y, our length is 12 minus d. D is this distance. And we can compare it with the total whole triangle, that is again 0 0.4 over 12. So this way we can calculate y value. So our y value would come around 0.9 meters. Sorry, 0.39 meters, almost 390 millimeters. If we calculate this value, it would be around 390 millimeters. So at the critical
What
section, our depth, yes,
when you are comparing, you are saying y over 12 minus d. What is the value of that d?
d this we calculated 312.5. The first step. Simply this take this 12 minus d in this direction, 12 minus d, and d put 0.31 to 0.5. 12 is 12, and simply multiply. Okay, so this way we have calculated this critical depth, the value of concrete at critical depth. So now the DC, the critical effective depth at this critical section, so that would be 390 minus 75 minus d by 2. So 25 by 2, half di of bar. So this would be our actual d at the critical section. This d value, this green portion at critical section. So this is about around 302 or something. Okay, so this way we can calculate this D value. Just now plug in this value in this question and we can calculate the applied shear. Any issue in this?
No, brother.
All right. So afterwards, we have calculated the shear, applied shear. Now calculate the shear capacity. So that is simply 5 VC. Formula phi is 5/6 times under root FC dash times BD. Now phi we have as 0.75 over 6. FC dash we have as 220 in the question given. B we are going to assume 1 meter width and that is 1000. And D we have calculated this, what this one, 302. So 302. This way we can check this applied shear against this shear capacity, and if our 5 if our 5 VC is greater than VU, that is okay. Otherwise, we have to devise the dimensions of the retaining wall of the stem. That we have to revise the retaining stem dimensions. So it is very much higher. Usually, it is shear capacity is very much higher than the applied shear. Only at the base, due to punching, it would be critical. Otherwise, shear is always or mostly satisfied. So they calculated shear like this and moment that's like this of stem. And for shear capacity, it was 190 kilonewtons and the applied shear was 130 kilonewtons. So this is okay. This is 5 VC. This is VU. So afterwards, what we have to do, we have to design the steel. So for retaining wall, the stem portion, we have this vertical steel and we have this horizontal steel. This black dots are horizontal and these lines are vertical. So where the backfill is, this steel is critical. So this is critical steel. Only this vertical steel is critical. So we are going to design this critical steel against the MU calculated before. We calculated MU this way, this one MU. We are going to design the steel of this vertical from this. So simply, if we have to design, what would we do? Simple calculate R is equal to MU or BD square, and from this R we know this rho as omega 1 minus under root minus 2.614 R over FC dash, and AS is equal to rho BD. Omega is equal to 0.85 FC dash over Fy. Simply just memorize these steps. We are going to use this very much. So plug in MU value, calculate R, plug in calculate omega value, plug in Bose's value in this expression, and calculate the AS for this critical steel. Afterwards, we have to determine also whatever this steel is, this one, this vertical steel, this is non-critical, but we still have to design this. So for vertical steel, away, away from backfill, I've written away from backfill. So that is simply we are going to use ACI criteria for that. The ACI criteria for that is this thing, 0.5 times the row value is 0.0015. 0.0015 times BH. Simply 0.0015 times BH. This is our minimum steel. Why we are taking this half? Because half we have already designed. This critical one we have designed already. Now we are only going to design this half portion. So we are multiplying this by half. So after this vertical steel, we have horizontal steel as well. Horizontal steel again we are going to use ACI value. So the ACI value is this again the same thing, that 0.0025 times BH and multiplied by half. So this much amount of steel we are going to provide this here as well as here. So we are halving. Why we are halving this also? Because half of the steel would be provided. 1/2 would be here and 1/2 would be here. Okay, just remember for horizontal steel our rho value is this. This is our rho value. And for vertical steel our rho value is 0.0015. This is for 0.0025. The rest BH is same. Any issue in this?
No, bro.
This way we can design the whole stem. So after designing the stem, we are going to move towards heel. So the heel thing is simpler. Only the stem is very much difficult. The heel thing is similar, simple. So we have this heel like this thing. So on heel, what is acting? This soil load is acting. That this soil load, this gamma times area of soil. For example, say the area of soil. The area of soil is 5.5 times this 2 meters. So gamma times area of soil. This much UDL is acting on the heel due to soil. Also due to this unit weight, self weight of concrete, whatever the amount is acting, that is gamma C into area of concrete. The area of concrete is again 2 meters times 0.45 meters. So these two forces are acting. The third force is acting as surcharge. The top surcharge what was acting. So S. So these three forces are acting on the heel. So for heel, simply we are going to calculate the shear force first. So VU for heel would be simple. Factor of safety multiplied by surcharge load. The factor of safety for surcharge is 1.6. 1.6 times surcharge load times the length on which it is acting. So it is we have 2 meters length of heel plus the factor of safety for concrete is I think 1.2 or 1.4. 1.2, okay. So the factor of safety for concrete portion is 1.2. Gamma of concrete is gamma of concrete times area of concrete. Area of concrete is 0.45 times this 2. Again, the gamma of soil would be 1.2 times gamma of soil into 5.5 into 2 area of soil. So this way we can calculate the total shear force acting on the heel. So charge value is 3. After this shear force, the bending moment for cantilever wall is simple, omega L by 2. So VU times L over 2. Simple LH length of heel over 2. So VU we have calculated in the above portion and multiply by length of heel we have 2 over 2. So simply we'll get the same value. No need to multiply any factor here because we have already applied these overload factors in the shear force. So if we apply again, so they would apply double. So no need to apply here. Just simply multiply by L by 2, length of heel over 2. Any issue in this?
No, bro.
Okay. So afterwards we have this toe. The last thing is toe. Second last thing is toe. So for
How
toe
do we
design,
get the steel in the heel?
how do we get?
The amount of steel in the heel. We use the same formula from before.
Yes,
Area of
we
steel.
are going to calculate this steel afterwards. Why not now? Because we know this d value here for heel and toe, the d value is same. That we are going to provide a base slab of same thickness, uniform thickness. So first we calculate the shear force for both heel and toe. Then we'll check the shear force against punching shear. And if it is satisfied, then we're going to use that d value to calculate this steel. Otherwise, we are going to revise the d value. So for after revising the d value, we are going to use this. So I mean to say that first we have to design both heel and toe and base slab. Afterwards, we are going to calculate this steel for heel and toe, because we are going to provide a uniform. We cannot provide like heel value is 0.45 thickness and toe value is 1 meter. So that would not be fine. Uniform thickness of base slab should be there. The method is same वैसे, M and then rho and then AS. So for toe, this is suppose a retaining wall. So we know this value as Y1 bearing pressure, and we know this value as Y2. Now for toe, the critical section is at the face of the uh, stem portion. So at the face of the stem, we are going to determine this Y3 value. Y3 value we are going to determine this at the face of the stem. So Y1 value we know as 155, I think. Y2 value was 25. So Y3 value we can either calculate it using similar triangles like before, or simply this formula is given. We have to memorize this formula, or either way we can use similar triangles to calculate this formula. So for where is toe? So this somewhere in the slides it is also written, but here it is written that simply y2 plus y1 minus y2 into b into x minus b minus x1 over b. So this way we can calculate y3 value, the ordinate of this y3 value. Okay, so after calculating this y3 value, we are going to divide this into two triangles. This one. The first one is this red triangle. The second one is this blue or black triangle. Black triangle. Okay, so we are determine this. We have divided this into two portions. So we know this length of toe is e is equal to 1 meter. This is the length of the toe. We know this as 1 meters. So for heel, what we are going for moments in sorry for toe for moments. What we are going to do, we are going to determine the area of this triangle and multiply the area of the triangle with their moment arms. For example, this moment arm of this would be from the face of the stem. This would be t over 2t over 3, 2 times t over 3, and for this smaller triangle it would be t over 3. Simple. We are going to calculate the area of the triangles, multiply the area of triangle with the moment arms. We will get the applied moment for the O portion. So the mu value would be uh, 1.7. I think this factor of safety is 1.6. Sorry, 1.6. So our factor of safety is 1.6 for these bearing pressures. So 1.6 times the area of red triangle. So what would be the area of red triangle? Half into base into height. 1 by 2 into base. Base we have as y1. We have the base of the triangle as y1. And what is its height? We have height as t meters. The height of the triangle is t meters. So this is area of the triangle times its moment arm, 2t over 3. Where the t value is 1 meters, the y1 value is 155 kilopascal. So this way we can get the first red triangle area. The second is the black triangle area. That is again the same 1.6 factor of safety, half into base. Base now we have as y3. Height is again the same t. And again the moment arm is t over 3. So this way we can get the second triangle area. Now some concrete load is also acting. These pressures are acting on the top, towards top. These bearing pressure acting towards the top. The concrete weight is acting on in the bottom direction, and also the front fill is also acting in the bottom direction. So we are going to ignore this front fill. We are only going to take this concrete weight. So the concrete weight we are going to assume with a factor of safety minus 0.9. We are decreasing it for conservative design. So 0.9 times concrete area. This is a rectangle, so concrete area would be simply 0.45. It is width into t into gamma c unit weight of concrete. Gamma c into area. Simply the formula is again the same. Gamma c times area of the concrete. 0.5 into t is the area, and gamma c is the unit weight times its moment arm. So it's a rectangle. The moment arm would be simply half. So t by 2. Okay, so this way we can get the moment arm for the moment for toe portion. The second thing is the shear for toe portion. For example, if I draw the same diagram larger, this is y1, this is y3, this is triangle 1, and this is triangle 2, and this is our face of the, this is our retaining wall, this is our face of the retaining wall. So shear, the shear value of the toe portion is again acting at d distance from face of the stem. First calculate d value. The d value for this now would be like this. 0.45 is its width. For toe, the width of the concrete is 0.45. So 450 minus 75 minus half dia. So this way we can get this d value. This is 362, I think. 362, something like this. So this way we can get this d value. Now for again we are going to for shear force, we are again going to calculate the area of this triangle. But now we are going to take only this area for triangle 1, only this area, not this top portion that is away from the D. So what would be its area? 1.6 times half. We can calculate the area of this large triangle. The this one, this is we know as T, and we can name this as TS for thickness for shear. So the larger triangle, this is the larger triangle, this one, the whole triangle. The whole triangle area would be simply half into base t into height y1. This is the larger triangle area. From this we have to subtract this small triangle area, this yellow triangle, this one. So its area would be simply half into base. Now the base of this is this is its height. The height of this is y. The base is this x value. This x value. We can use similar triangles to calculate this x value. So x over d, the smaller triangle, is equal to y1 over t, the larger triangle. So base over height is equal to base over height for similar using similar triangle. So x value simple is d into y over t. This is our base. X is d into y over t. So I plugged in the x value here. This is the base of this small triangle, and the height of this small triangle is d. Okay, this way we can get this triangle area, the highlighted triangle area for the first triangle. Now again we have to do this for the second triangle plus 1.6 times. Now if we assume this value as was this value as y, this ordinate as y. So we know using similar triangles, this is y3. Y over its base, the base of this y is this green triangle. Y over base is ts is equal to y3 over total this base t. So the y would be our ts over t into y3. So for some smaller triangle, our area is simple: half into base into height. Half into base ts into height is we have ts over t into y3. And the last portion is concrete minus 0.9 times gamma of c into area of concrete, 0.45 into ts. Now we are going to use ts here, not t. So this way we can get this shear. In shear, there is no need for moment arm, so just simply these values. Any issue in this? Simply you can memorize this, but if you understand this, you can easily drive this on in the paper. Any issue?
No.
Okay, so the last portion for this is base slab. So for base slab, we are going to use VU as maximum of toe and heel. So whatever the shear applied shear of toe and heel was, we are going to take its maximum, and we are going to calculate its shear capacity as 5VC is equal to 5 or 6 into under root FC dash. Remember this formula BD. So 5 we have 0.75 over 6, under root 20, V we have 1000, into D we have 362. This one is 362. So if 5VC is greater than VU, then that's fine, okay. No need of something doing anything. If 5VC is less than VU, then we have to devise thickness of base slab or base slab. So what I said at the start, that thickness of base slab is not very important because we can design this in the last step as well. So in this question, it came less than 5VC. Our 5VC was 228 kilonewtons and VU was 311 kilonewtons. So in this case, if 5VC is less than VU, simply just plug in the VU, calculate, plug in VU here. That VU is equal to 5 over 6 times mass dash into D, and calculate the D value, device D value. So putting here like 311 into 10 to the power 3, that is in kilonewtons, times 0.75 over 6 times under root 20 times 1000 times D. So calculate D value from here, and using this D value, now we calculate this actual D value. D value this was this D value is like, I think almost 480 millimeters. Was came 480. So now our D value is 480. Now we are going to design the steel for heel and steel for toe. Steel for heel was simply R equal to mu over BD square. Take this mu of heel and D as 480. This D. Why we didn't design the steel before in the heel portion? Because we were not sure about this D value, that if the D value is changing or not. If the D value is changing, then our steel area would decrease. So that's why we are calculating this steel at the last. Then rho is simply omega 1 minus under root 1 minus 2.614 r over FC dash. And the last thing is AS is equal to rho BD. Similarly, for toe, again we have to do the same thing. Just simply use the MU for toe Mu for toe we have to use here, and Mu for heel we have to use here. And this way, and the last we have to design the distribution steel. So the distribution steel is simply 0.0018 BH for grade 420. If the grade is 300 or 280, this is 0.002. Grade 300 or 280. So simply this way we can design the distribution and top and bottom steel for this. So how we are going to uh, put the steel in this retaining wall? So this is our main steel. This way our backfill wall. This is our main stem steel that we calculated using the MU. This is our red one is our ACI minimum steel that we calculated from rho using 0.0015 using rho 0015. Now these are our horizontal steels for stem. These we also calculated from ACI using rho as 0.0025. Remember these rho values. The rest is same, the rho BD or rho BH. And for toe, we are going to provide steel at the bottom. This way we are going to provide the steel at the bottom of the toe, and its value is this one. Steel from toe, for example, if I write this as 2, so this value is 2. And this, for example, this steel area of steel was 1, so the heel area of steel would be provided here. This is 1. And finally the distribution steel, it would be provided like this on both faces. So if I call this distribution steel as 3, so this both are 3. Okay, this is how we are going to detail the retaining wall. Any issue in this?
No, Hamza.
Okay, so this is all for retaining wall. The second portion is tank design. Retaining wall is simple. Just first you calculate the dimensions, calculate vertical and horizontal forces. The third step is apply the 3 checks, and the fourth step is the design of components: design of stem, design of field, design of toe, and design of base slab. So this way we can get design the whole retaining wall. If we were asked about gravity wall only, then we are going to only use dimensions, forces, and the stability checks. No need for this toe steel wire design. So for rectangular tanks, now this rectangular tank is very much similar to this retaining wall design, because in this rectangular tank we are going to design 2 times retaining wall and 1 base slab. We are going to design 3 things in this also. So this is suppose the retaining wall of the tank, and here this is water, some water, and this is suppose our base slab, and this is suppose our support for this rectangular tank. So it is given that our length between inside faces of wall is 3.5 meter, short walls. So that is 3.5 meter. The height of the walls is 2.5 meters, and the thickness of the base slab is 0.2 meters, 200 millimeters. The thickness of the walls are also 0.2 meters. and the height of the sport is 75 millimeters, and the width of the sport is, I think, 400 millimeters. Yes, 400 millimeters. So this is 0.4 meters. And if it isn't shown in plan, so in plan, so these are our retaining walls. So in plan, the short dimensions are 3.5 meters, like shown in this way, and a longer dimension is 6 meters. So we have two walls of 3.5 meters, two walls of 6 meters, and a base slab of 0.2 meters or 200 millimeters. This is all the data given, and FC dash and FY also. FC dash and FY are given as 30 and 300. FC dash is equal to 30, FY is equal to 300 megapascals. So this is the data given of the rectangular tank. First, we have to design the walls. For example, first we have to design the long wall. So for long wall, first we calculate the K value. K value is simply Ly over Lz. Ly is the longer dimension, Lz is the height, Lx is the shorter dimension. This 3.5 meter is the Lx, shorter dimension, 6 meter is the Ly, longer dimension, and the height of the tank is Lz. So these are three things. So Ly over Lz, we have 6 meter, Lz has 2.5. This comes as 2.4, this is greater than 2. So now we have for retaining wall three cases. First case, second case, third case. If K value is greater than 2, that means one-way slab we have to design vertically. If K value is less than 0.5, again we have to design one way but horizontally. And if K value is lying between 0.5 till 2, we have designed two-way slab. So these are three cases. K value greater than 2 one way vertically, K value less than 2 less than 0.5, this is one way horizontally, and between them is two way. What does this mean, one vertically and horizontally? For example, we have in this case 6 meter width and 2.5 meter height. So we have this kind of wall. 6 meter is its width, 2.5 is its height. This long wall. So the always this slab, the span of the slab is always the shorter direction. The span of any slab is always the shorter dimension. So the our span is in this way, in this condition vertical. So that is why we are saying that it is one way slab vertically. Similarly, if L over Y's ratio was less than 0.5, so our wall would be like something like this, that our height is much more higher. For example, this is our 10 meters and this is our 4 meters. So Lx over Lz ratio is 4 over 10, that is 0.4. So it is less than 0.5. So it means one lead wall in horizontal direction. And similarly, we can say that the span is between the smaller part, smaller direction. So this is one way wall in horizontal direction. If it is in between that, it is simply two-way wall. So if we have one-way wall, we have suppose one-way wall. So after that, we are going to calculate pressure P. Pressure is simply gamma times H. The gamma of water is 10, H height of water is 2.5, so that is 25 kilopascal. After pressure, we are going to calculate force, that is F. The force is, if I draw this like this is our wall. This much amount is water is acting on this, and the pressure is gamma H, the bottom coordinate. Gamma H, this thing. The force is this resultant force acting. This is the area. So this is the force. This is the force. Force is the area of this triangle to half into base. Base is 25. The upward the pressure calculated into height is 2.5 meters. So this is 31.25. The last thing we calculate the moment. So the moment is simply force times this moment arm. This moment arm is 2.5 over 3. Uh, Simply. So force 31.25 into 2.1. Sorry, 2.5 over 3. So we calculated the force, we calculated the pressure, we calculated the moment arm directly for one way. For one way, it is simple. We can just calculate these values directly. After calculating this moment, this is allowable stress moment, not factor moment. So we can calculate factor, that is 1.7 mu. Now we are going to use factor of safety as 1.7 because it is retaining liquids. So 1.7 mu. The D value for this wall would be like, this is our wall. We are designing the vertical steel because it is spanning vertically, so the main steel would be vertical. Remember, along the span, the main steel is provided. It is spanning vertically, so the main steel is vertical. So our vertical steel is inside and our horizontal steel is outside. Why? Because we want to provide more cover to this vertical steel because it is water. So if there is some sort of crack or something, it would cause the main steel to rust if sufficient cover is not provided. So we are providing the main steel inside. Or in all cases we provide it outside, but here in this case we are providing it inside. So the D value for this would be something like this. D value. D value would be 200 millimeter is the thickness of the total wall, minus 40 millimeter is the cover, minus this horizontal steel. We can take this as number 13 minus the dia of this vertical steel. So the main steel. So we can take this main steel as more reinforcement. So we can take it as 25 millimeter over 2. And B value we already know as 1000 millimeter square. Okay, in this any issue in this portion? Okay, so now we are going to design uh, these steel values, the area of steel using both methods, ESD as well as USD, ultimate stand design. So now we are going to design for both these two methods. For ESD, our moment is simply this. For example, this is approximately 26. So our ESD, our moment is 26. For USD, our moment is 1.7 into 26. So that is 442, something like this. Now we are going to design for both these two movements. After calculating these movements, R value is simply m over bd square. We know b, we know d. We can calculate R value. R value is m over bd square. So we know b and d the same. For example, the R value for this first steel was 1.43. Now in case of ultimate, we can use rho value as omega 1 minus 2 1 minus 2.614 r over fc dash, simply the usual procedure. As equal to rho bd, we can calculate like this, simply calculation. For this working stress method, we cannot use these formulas because fc dash is the ultimate stress, is not elastic stress. So we are going to use these charts. So these charts are given for working stress. This is for fc dash 20 megapascal. This is for fc dash 30 megapascal. We have 30 megapascal. And our RW working R is 1.43. So 1.43. So approximately here. We'll move to this curve for 140 megapascal. If you check here, Fs is equal to 280 to 350. Fs is 140. So our steel is 300. So we are going to use this curve, 140 curve. If it was 420, we are going to use 168 curve. So now our steel is 300. So this is something like this. Our rho value, the steel ratio rho for this is 0.011, 0.015. Rho is simply 0.015. So, and ES is again rho BD. Simply the difference is the rho value we have to check from chart. In this case, we have to calculate the rho value from this table, from this equation. Charts are also present for this ultimate strength, but we can simply use this formula. It is more accurate. Okay, so the ES value we are going to select is the largest one of these two. The larger one we are going to select. This was main vertical steel. Now we are left with the vertical steel in the other direction, the non-critical vertical steel. We designed this one. Now we are going to design this one. This one we are going to design now. So this non-critical vertical steel is simply the ACI. So vertical steel non-critical. That is simply 0.5 times 0.0015 BH. So simply the same quotient for retaining wall we are going to use here. 0.0015 BH and half because it is for half steel. And horizontal steel, again we are going to use the same as retaining wall. So horizontal steel would be 0.5 times 0.0025 into BH. Half mean 0.5 means that 50%, this much amount will be provided on one side and this much will be again provided on the other side. This much amount will be provided here and again this much amount would be provided on this side here also. Okay, so we are designing this movement. Last thing we have to check the shear. The shear is simple, that whatever the force was for we use factored force 1.7 into the force F. So our force was 31. 1.7 to 31. So we'll get this applied shear. Best is 5 EC. That is again 5 over 6 under FC dash PD. Plug in the values. You'll get 5 EC. 5 EC should be greater than PU. Any issue in this long wall? It is almost exactly the same as retaining wall. Okay, no issue.
No trouble.
All right. So the second thing is short wall. We have designed the long wall. Now we are going to design the short wall. Then we are going to design the base slab. Then we are finished. So for short wall, first calculate the K value again. The K value is Lx over Lz or Ly over Lz. So Lx, we have 2.5 meters. We are going to 3.5 meter. We are going to assume 100-meter extra width in both. It was 3.5 and 2.5, but now we are going to add 100 millimeters in both these lengths. Why? Because we are going to achieve two-way action wall. So two-way action, we need 100-meter more. That means that we are going to take it till the middle of the wall. In the one-way slab, our spans are like this. Our spans are between from the faces of the wall to the faces of the wall. For two-way, for example, this is a two-way wall. The span would be between this to between this. I mean that 15 meter add from this, 15 meter add from that direction. We can get the two-way action. Simply add 100 meter in both directions. 100 here, oh sorry, 50 here, 50 here, and in this direction as well, 50 and 50. So it is 1.4. It is less than 2. That means it is two-way wall. So for two-way wall, we are going to design this wall in two directions. First, we are going to design in horizontal direction. Then we are going to design this in vertical direction. So our pressure is again same gamma into h, that is 10 into 2.5, 25, and the force is again same, that is half into gamma h into h, so it is 31.25. These forces and pressure are same. First, horizontal direction. Now we know that this tank is fixed on both directions by this wall. That this is, for example, this is a tank. In horizontal direction, it is fixed on both sides because there are retaining walls on both sides. So that means that whatever our bedding moment diagram would be like this. That we would have some mh negative moments, matlab, horizontal negative moments, and we would have some mh positive moments. So in horizontal direction, we have to design two moments, mh negative, mh positive. So we are going to design these both two moments because it is fixed on both two directions. So we are going to design this moment. So it is simple. Moments are simple. The formula of moments is simply, for example, mh positive is simply ch positive, the quotient of this moment times the pressure times this length, this much length. So this much length we know this is Lx or 3.6 meter because it is horizontal. So 3.6 square, Lx square. So Ch positive. We can get Ch positive from this graphs. These graphs are given for top edge unsupported. Our case is top edge unsupported. The second graph is given for top edge simply supported. The third is given for top edge fixed end. So our question is from top end uh, free. So in this case, whatever is our Lx or Lz value, Lx or Lz value is 1.4. So for 1.4 value, we are going to check this Ch positive and we are going to determine this moment coefficient. So the moment coefficient is this one, C. So for Ch positive curve, this curve is for Ch positive. Our moment coefficient is 0.016. So 0.016 into 25 into 3.6 whole square. So this way we can get positive moment, and the ultimate positive moment MUH would be simply 1.7 times MH positive. Okay, simply whatever the value came above multiplied by 1.7. Now after that we are going to need the D value for design of steel. So the D value is like this for horizontal steel. Like this is our retaining wall. So we are going to provide this horizontal direction steel because this short wall, this is 3.6 meters. This is like this short wall. So whatever the D value is like this. Because it is horizontal we have provided direction. We have provided inside DH positive 200 minus 40 per minus half diode bar. So we can take the diode bar as, I think, something 13 or whatever. So 13 by 2 we can take. What they have taken. So horizontal steel they have taken diode bar as 12. So 13. That means they have taken 13. We do not have 12 diode bar. So we have to take 13. So we have to take this where DH positive value, and for afterwards we have no we know the value of B, that is 1000 millimeters. So using this, again we have to do the working stress and ultimate stress design using these two moments. We have MH positive here, and MUH positive here. So using charts, this one for charts and this one using direct formula for rho, we can calculate the area of steel required in horizontal direction and provide the larger one of these two methods, working stress or ultimate stress, the larger one. Okay, again for vertical direction, again the same thing we have to use, because we now know that in vertically the top end is free. So that means this is a cantilever wall like this. So only MV negative would be present. That only negative moment would be present. There would be no positive moment because the top end is free. If the top end was fixed or hinged, then there would have been a negative moment. But now in this case, there is no negative moment. Sorry, no positive moment. Okay, oh sorry. We have designed only positive here. This is only positive. Now we have to design first before going to moving towards vertical. We have to design negative moment for horizontal before. MH negative is equal to CH negative times P times 3.6 square. So CH negative we can get from these curves. This is for CH negative curve. So approximately are like this, something like I think 0.32.33, 0.032 or something like this into 25 into 3.6 square. This is MH negative. MUH negative would be 1.7 times MH negative. The same thing. Then DH negative, because it is horizontal also, so the DH negative would be same as DH positive. And again we have to use working stress design, ultimate stress design to calculate moments. This is MH negative and MH positive. So for short wall we have two direction, positive and we have two direction, horizontal and vertical. And for horizontal we have two steels, positive and negative. So this way for horizontal direction is finished. Afterwards, now we are going to move towards vertical. So for vertical, only MV negative is present. Why? Because I said that this is free at top, so only MV negative is present. So MV negative would be simply CV negative into P into, now the height of this vertically, in the vertical direction, the height is 2.6. Now we are going to multiply it by 2.6. CV negative coefficient we can check from these tables. So CV negative chart is, see, this is CV negative chart. So approximately 0.0057 or 58. So 0.0057 into 25 into 2.6 square. M ultimate V negative is 1.7 MV negative, and B BV. Now BV would be simply 200 minus 40 cover. This is BV, vertical direction steel. So that 200 minus cover minus die of horizontal bars minus half die of vertical bars. So this way we can get the vertical steel uh, dV. This is dV. And finally apply USD and a working stress design. Calculate steel for both methods and provide the larger one. So any issue this way we can design the short wall. So in short wall we have horizontal direction, we have vertical direction. This is two-way. For two-way walls we have to design this way. For horizontal direction we have to design MH positive and MH negative. For vertical direction we have to design only MV negative because it is free at top. Free top. It is fixed on both direction horizontal. And both moments we have to design by USD and ASD. USD and ASD and USD and ASD. So this way we have to design the steel for short wall. Any issue in this?
No, Hamza.
Okay. So one thing was left, I think, the shear capacity. They have not applied shear check. Okay, shear capacity was, I think, somewhere. Shear capacity is also checked. You can check the formula. It is simple, quite. The shear capacity of both walls are checked, and it is simple, quite. So afterwards, the last thing is base slab. So now we know that the base slab is uh, 3.7 meters horizontally in x direction and 6.2 meters in this direction. Why we have increased from 3 to 3.5 to 3.7? Because they were 200 millimeter wall also. So we are adding the wall weights in this also wall because the base slab is also under the wall as well. So 3.7 meters in x direction and 6.2 meter in y direction, the base slab. First calculate K value. K value is Ly over Lx. So 6.2 over 3.7, it comes 1.6, 1.68. 1.68. Is it less than 2? That means we have to design this as two-way as well. That it is two-way slab. The bottom slab is two-way. So for two-way slab, again, we are going to use the same things. We are going to use, we are going to, for X direction, we are going to design positive steel as well as negative steel. And for Y direction, we are going to design the positive steel as well as negative steel. These four steel we have to design for this base slab. So for first, we have for X direction or short span. Short span, that is X direction. For X, first calculate alpha value. So alpha X is equal to K power 4 or 1 plus K power 4. Remember this formula, it may not be provided. So K is 1.68 over 1 plus 1.68 power 4. So that is 0.89. So this means that 89% of the movement, 89% of the total movement that would be generated would be transferred to the short span. That is why the short span is called critical and main is force span is avoided there. Because almost all movement is transferred to the short span. Only 11% would be transferred to the longer span. So short span has 89%. Alpha is this. Now the second thing is ZC, critical depth of height, critical depth of water. So the formula ZC is Lx or Ly, whatever the direction we are designing, and alpha x over 24 beta. So Lx we know as 3.7, alpha x we know as 0.89, beta we do not know. Remember, for short span, it would touch long wall. The short span would touch long wall, and if the long wall is one way, we are going to use beta as 1.1 over 6. Okay, so if the long wall is one way, the long wall is two way, then we are going to uh, we check in the long span. But if the long wall is one way, we are going to use beta as 1 over 6. Why? Because we know that moment is equal to half into base into height, gamma z into z. This is the base into height into its moment arm. So that is z over 3. This is the moment arm. This is a base into height. That is gamma z cube over 6. So the coefficient of moment in this portion for one way is 1 over 6. The coefficient is 1 over 6. So we are using beta here 6. So 3.7, 0.89 over 24 into 1 by 6 square root. Answer is 1.745 meters. So that means the critical depth of water for tank is 1.745 meters. So for example, this is our tank. So a tank is not fully filled. It is filled till 1.745 meters. This is the critical depth. Let's see. This is water. So afterwards, we have to calculate simple span moment, that is m naught x, that is alpha over 8 into gamma z into Lx square. So this is simple span moment. Alpha we know as 0.89 over 8 into Lx square we have as 3.7 square gamma z. Now if you check this portion, so here it is gamma w and below it is gamma concrete as well, the sulfate of concrete. It is of 200 meter, 0.2 meter thickness. So we are going to use them separately. So 1.745 into gamma of water 10 plus 0.2 into gamma of concrete 25. This way we can calculate simple span moments. So it is 26.577 plus 10.615. That is equal to 34.2. So this is where we can calculate simple span moment. So now for positive moment, that is mx positive, that is equal to m naught x minus mx negative. If you subtract the negative moment from the mx positive from total moment, simply span moment, so we'll get the positive moment. So the negative moment formula is beta into gamma z cube. Remember this formula. This is beta into gamma z cube, formula for negative moment. The positive moment would be mx positive would be 26.577 plus 10.615 minus beta into gamma z cube 1 by 6 into gamma is 10 into z cube 1.745 cube. Here no need to apply concrete, just simply use the water one. Okay, so this way we can calculate the mx positive moment, the positive moment for this portion, horizontal x portion. Afterwards, we have to calculate mux positive, ultimate positive moment. So simply multiply, this is because of water, so multiply this by 1.7. This is because of concrete, multiply this by 1.4. This is because of water, so multiply this by 1.7. Simply multiply 1.7 with 26.5 plus 1.4 into 7.615 minus 1.7 into this whole thing. So what you'll get this, you will get this ultimate moment. So after getting this ultimate moment, calculate the value of d. The d value is, this is because it is base slab. So Our short span. We are designing this as short span. So short span would have steel inside. Short span is critical span, so it would have steel inside. So our D value is this thing. Dx positive, that is also equal to dx negative. Both are same. That is 200 minus 40 minus this 13 minus 13 over 24, 13 over 2. So this way we can get the D value. Now use ESD and USD to design the steels. Okay, an issue in this. This way we can design positive steel for short span. We have designed only positive steel for short span. Now, as I said before, we have designed this positive steel for short span. Short span is the X span. Now we are going to design the negative steel for short span. So mx negative, that we can simply take whatever the value of moment was in the long wall. This is a short span. It would meet the long wall. So the moment in the long wall was 26. The moment in long wall was 26. So whatever the moment in long wall was, we can simply take that value for negative moment. The moment in long wall was 26 long wall moment. And mux negative would be 1.7 into 26. And dx negative is the same as dx positive. That is simply that. And you can design this by ASD and USD, both methods. Any issue in this short span? No. So the last thing is the long span. The very last thing is the long span. So again, in the long span, we have to design the my positive and my negative. But the long span is the y span. So we are going to design two moments in this case as well. So my positive and my negative. So first of all, again the same procedure. Calculate alpha y value. The alpha y is 1 over 1 plus k power 4. So alpha x was 0.89, so it would be 0.11. Sum of both these would be 1 always. So that means only that percentage moment is going towards this alpha y direction, long span. After alpha y, calculate zc. Zc is ly times alpha y over 24 beta. Now in this case, beta value you would take whatever the CV negative value was for short wall, because the short wall was two-way. So for two-way we take whatever the CV value was, CV negative value was, and take this as beta value. This one. 1 minute, Azan is. For negative moments, again the same procedure we have to apply. First, we'll get simplified negative moments. That would be alpha over 8 times Ly square. So Ly we have 6.2 square times gamma into gamma of water into Zc. The Zc value is suppose the Zc value here is 1.687. Actually, it is a bit different. You can try this. So this is for positive. So 1.687 plus zero point 0.2 into 25. This is we can get simple span moment for positive direction. Then simply what would be my positive? That would be m naught y minus my negative. So m naught y we have this whole thing minus m naught. This is beta times gamma z cube. So beta we know as 0.058 CV negative. Gamma we know as 10, Z no we know as 1.687. So calculate this value and get My positive. So for MUY positive were factored, multiply this water one with 1.7 factor, the concrete one is 1.4 factor, and this water one again with 1.7 factor. Calculate the D value and use USD and ASD to design this. The D value would be like this is our positive, this is our largest span. So the largest span would have steel in the outer direction. It is not critical. So our D value would be something like this. dy positive and dy negative would be same, and 200 minus 40 minus 13 over 2. This would be our D value for this case. Similarly for negative one, and simply we'll use the my negative from the short wall. The short wall had maximum negative moment as MS negative was 10.044 and MV negative was 10.26. So the larger one we can take from these two negative moments. So the larger one is 10.26. So 10.26 MUY negative is 1.7 into 10.26. DY is equal to DY positive. That is same. Again ESD and USD. Apply method both calculate the steel. So this way we can get design the long span for the base slab. An issue in this, and up till this we are finished with this per tank. This we were not taught, sir. Didn't discuss this portion. It is actually quite simple if you focus short wall area. Simple this area they have taken this as area. Floor area they have taken this area. Sports they have taken these two sports. Calculate total area. This is total area. Zi is the distance from bottom level to the middle of the section. For example, our sports were 75 millimeter. So the middle of the sport would be 37.5 millimeter. This is the floor is at 275 plus 200 by 2. This would be the middle of the floor. That is 100 plus 75, 175 millimeters. Similarly for this wall, multiply into A into Z. Calculate I simply BD cube over 12. So the B value is horizontal, D is the vertical. For example, for short walls, zero point 0.2 into 2.5 cube over 12, like this. And A into Z minus Z bar. Z bar is summation AZ. This summation AZ divided by this summation A. So this is Z bar, centroid of the area. This is the total area. This is the total moment of inertia. Add this one and this one. Calculating this total moment of inertia, we can get maximum pressure we know as already 25 pressure force. Now 31.25 we calculate pressure force for this was per unit length, and if you multiply it with the length of the wall 6, we'll get this total pressure force. And it acts at centroid. That the wall is 2.5 meter high, so the pressure force would act at 2.5 divided by 3 at a centroid. So this 0.833 is 2.5 divided by 3. 0.275 is 200 millimeter, yeah, slab plus 75 millimeter support. Eccentricity is simply subtract from centroid this location, and moment is simply P into it. This is just like how we calculate the bearing pressure in retaining walls. P over A plus My over I, and here is P over A minus My over I. This only minus sign is different. This is M, this is I, and this is Y. Y distance from neutral axis to the extreme fiber. So neutral axis at 0.743, extreme fiber is 2.7. So calculate this. Calculate the average of top and bottom stresses multiplied with the wall thickness. We can get tension force in kilonewtons. We divide by stress, allowable stress. We can get the tension area of steel. So this way we can get the area of tension in steel. So this is how we can design the retaining wall, water tank. Any question?
No, brother.
So this is for DOS concrete portion. If there's no question, should we end?
Yes, brother. I have one question. It means by this part, these two questions will come. One from retaining wall and one from tank. And what about
Yes, yes.
steel part? Is how many
Steel part,
questions and which
steel
part?
part actually uh, put more focus on membranes part. That is example 9.1, 9.2, and 9.3 from uh, stringer design, yeah, deck slab design, and floor beam design. Because last time only 5 marks were from membrane part. Now this time I think a question of 15 marks would be from membranes part. So, and those questions are quite larger. Actually, floor beam question is quite larger. It is simple, but it is quite larger, I think. So after that, 5 to 8 marks part would be from Sir Rashid part, and base plate. We already have the base plate in midterms, so I think from moment connection it may come. Just remember how to make the well design. Sir gave it more focus in the last lectures. How to uh, well design this. So this is example 9.1 for stringer design, and these examples are quite larger. So 12 to 15 marks would be from these examples. Here it is finished. And example 9.2 is for stringer as well as floor beam design. So this is stringer as floor beam design. Okay, this is not floor beam design. Floor beam design is for example 9.3. So 9.3 and 9.4 are important. So this is exterior interior stringers and floor beams. So these are important. Anything
Okay,
else?
brother.
Can you share this video with us?
All right, all right. I'll share.
But how you share it?
Recording?
Yeah, I know you are recorded, but I mean, you will make a group and share it, or
I'll share with Jayani or Nazan, and they can forward just like the link.
Yeah, yeah, yeah. Okay, I will.
Thank you so much, bro. Thank you so much.
Okay, no